Okay, thank you, John. For this little session, I thought I would give just a bit of a sampling of some of the things we've been working on over the last few years. They don't really necessarily have a coherent pattern, but a lot of the work is based on our large cohort studies. So I thought I would just take a minute and go over those. Many of you are familiar with these. Basically, we have three large cohorts, although we have now enrolled about 70,000 women in Nurses Health Study 3, which has a little bit different design. But basically, in the Nurses Health Study, 121,000 nurses, where we started collecting dietary data and other lifestyle data in 1980. And we've been following people along with update of diet about every 4 years, along with physical activity. And every 2 years, we send out a questionnaire that updates information on health outcomes, BMI, lots of other potential risk factors. Along the way, we've collected blood samples starting in about 1990. We've on a major subsample collected blood from participants again in 2000. And we've collected lots of other information. I won't go into that, but tracking almost all diseases in terms of incidence and mortality. Health professionals follow-up study, same design, men though, and Nurses Health Study 2 is pretty much same design, but started women when they were younger, 25 to 42 years of age, because a lot of the epidemiology was pointing to earlier life as being ideologically important for breast cancer and many other diseases. So that's where we are now. We've lost all our federal funding, but we're struggling to keep following people. It's actually a pretty big challenge right at this point, and we don't know where it's going. I'm going to first say a few words about a study we published in BMJ a little over a year ago. Our postdoc, Yi-Wan, did this work looking at carbohydrate quality in relation to weight change. And for this analysis, we included healthy women with all available data and healthy men. About 136,000 participants were in this analysis, which gave us a lot of data to look at this question. And what's important here is that we looked at weight change over time as a function of change in diet over 4-year segments during this follow-up. So the statistics were a little bit complicated. I won't go into that, but basically it's looking at change in diet versus change in weight over 4-year intervals. Very quickly, this is what we found. The 3 colors here represent the different cohorts. It was reassuring that we found almost identical results in all 3 cohorts, which of course strengthens the conclusion. And the numbers are huge for looking at weight. So yeah, confidence intervals are all really tight. Total carbohydrate, we can see up at the top there, was slightly positively related to weight gain or weight positively related to change in weight over time. But I think, as we all know, total carbohydrate means almost nothing in terms of health outcomes, because it's really the quality of the carbohydrate that's important. And that's what this emphasized. We did look at carbohydrate quality in multiple ways here in sources of carbohydrate. This next cluster of slides of data points there, it's sort of hard to point from this this direction, but it's we looked at glycemic index, positive associations with weight gain, glycemic load, similarly positive associations in all 3 cohorts. Then we looked at fiber, carbohydrate in different forms, and as you can see there, fiber, acknowledging that there's a lot of heterogeneity there. Inversely related, starch, quite strongly positively related to outcomes, added sugar, positively related, natural sugar, basically mostly from fruits, weakly negatively related, total glucose equivalence, which we have just started to use that variable. It's basically the glucose from starch or as glucose from other sources, and putting these all together in a variable. And that produces quite strong associations when we look at glucose equivalence. Interestingly, fructose equivalence, that next cluster of data points there, are really null. And that by itself is pretty interesting, because there's a group of people who believe fructose is the evil factor. It's really not. From everything we've looked at, maybe some of the studies show if you take massive amounts in fructose, you get some adverse changes, but nobody's near that level of intake. Then what I think is very practical, carbohydrates from different food sources, which again, these are going to be heterogeneous, from whole grains, inversely associated, refined grains, positively associated, from fruits, inverse, and from non-starchy vegetables. Of course, there's not a lot of carbohydrate there, really, inverse, and from starchy vegetables, mostly potatoes, positive association. So that's there's in the paper, if you want to look at, there's a lot of data there. We've also looked at this instead of continuous variables as categories. Those continuous variables represent some people who reduce their intake, some people who increase their intake, and the relationship is basically pretty linear. They're just, for example, the second little mini figure there, glycemic index, there was with a reduction in glycemic index weight loss, with increase there was weight gain. So it's basically the associations were quite symmetrical in going up or down in terms of intake. This is a two-dimensional figure, and my simple mind likes to think of carbohydrate quality as sort of two dimensions, and recognizing that can make it very multi-dimensional. But I think this addresses somewhat Mary Ann's comments in the last session, that glycemic index is really important, and that's one dimension, glycemic index or glycemic load, and the other dimension is cereal fiber or total fiber or whole grains, essentially capturing that other dimension that comes along with a lot of minerals, vitamins, and fiber. And we can see, looking here again at weight change over 4 years, the people who decreased their glycemic index and increased their fiber or whole grains, however we did it, actually had the lowest weight change, or actually lost weight during that period of time. On average, the whole population was gaining weight at about 0.5 kilogram a year. So on average, basically everybody's going up, but there's a lot of variation. We then stratified the analysis by BMI, and this summarizes what we've seen in other studies too, but basically carbohydrate quality, the effect of carbohydrate or carbohydrate quality on changes in weight is very modified, strongly modified by their baseline BMI. And that could be due to, given that picking people up in midlife here, everybody's been exposed to an obesogenic environment to various degrees, but if you haven't gained weight, or you haven't gained weight much time, your BMI is still low at age 40 or 50, it means you have some immunity against unhealthy diets. And it could be for genetic reasons, cultural reasons, other factors. But if you look at glycemic index there, as you can see, the adverse effect of glycemic index was much worse in people with a BMI above 30, and there was much less increase in people with a BMI under 25. But still, everybody was moving in the same direction. So to me, this is sort of important, because I think there's too much emphasis on these personalized diets that some people will benefit more, some people benefit less, but we rarely see things are going in opposite directions by a genetic factor or other factor like BMI. Basically, if everything is personalized, it takes away the main levers of public health, which are things like general education, social norms, taxes, restrictions, all those kinds of levers. So I think we want to be careful about personalized nutrition. There will be some examples where it can be useful, but if we go down that road too far, it will really, I think, be adverse, because it will disarm our main weapons. Anyway, you can see there that basically pretty much all our variables that were associated with weight change, like starch there in the middle, was basically, again, the effect was strongly modified by baseline BMI. Then we've gone on, this isn't yet published, but to look at genetic risk, we have, for the same people, we had GWAS data from about 26,000 participants, and we have a lot more DNA, but it's still a bit of somewhat expensive to analyze that. So we could look at the genetic risk score for BMI and polygenic risk score. For those who are not familiar with that, you just look at all the SNPs and get the best prediction score. It's usually a little bit stronger than using the standard genetic risk score. But you see the same kind of interaction there. Glycemic index, there's modification by the genetic risk for BMI. The higher genetic risk, the stronger the association with weight change. And inversely for fiber, again, that interaction wasn't quite significant with the genetic risk score, but there tended to be interaction there. But interestingly, the baseline BMI was a little bit more powerful as an effect modifier than the genetic risk score here. And partly, we're still updating our genetic risk scores, adding more SNPs in, but baseline BMI is a lot easier and cheaper to get, interestingly. Another analysis we published a few months ago was looking at potato intake and risk of type 2 diabetes in our 3 cohorts, and then also something that we hadn't done before that we've called a substitution meta-analysis. And we did this in part because of the upcoming Eat Lancet report, and we got pushback last time because we emphasized whole grains over potatoes, and the potato industry obviously was not very happy about that. So we did this with diabetes is a very important outcome, and where we had about 22,000 incident cases of type 2 diabetes in our cohort, so we had a lot of power to do this. And this may be a little bit hard to see, but this is looking at the substitution analysis. And this is, in some ways, it's just comparing the two with the multivariate model, and then you have the 2 variables here, potatoes, whole grain, for example, and you compare the coefficients and calculate the confidence interval based on variance in both of those coefficients. So very clearly, right at the top there is substituting total potatoes with whole grains, and there's clearly an advantage to having whole grains over potatoes, which was why we didn't say you shouldn't eat potatoes, but try to convey an emphasis on whole grains where that's possible. Not that everybody has that option. But then we substituted boiled or baked potatoes, which were not as strongly related as total potatoes, but still the whole grains for mashed, baked, boiled potatoes were better for diabetes risk. And then French fries, which were most strongly related, the potato types with type 2 diabetes, again, substitution of whole grains, very strong. I would note in that top section up here, just use my notepad, and white rice didn't look so good here. That seemed to be the worst form of carbohydrate that we could see. And that, obviously, a lot of the world eats a lot of white rice, and I think that deserves some more look here in terms of type 2 diabetes risk. But in this data set, that was not, brown rice was better, but white rice really stuck out there. And then we went on to do the substitution meta-analysis. And it's sort of a simplified form of network meta-analysis. Basically, we took all the studies that we could find in meta-analysis of whole grains and type 2 diabetes, meta-analysis of potatoes and in relation to type 2 diabetes. And in my own mind, I always sort of look at, oh yes, whole grains are pretty consistently inversely related, and potatoes either null or positively related, therefore it should be that substituting potatoes with whole grains would be beneficial. And But this was just doing this in a more formalized way and taking into account the covariance of potatoes and whole grains, and using some sensitivity analyses because these were coming from different sources, the two separate meta-analyses. And you can ignore those two columns to the right about number of studies. Somehow that got messed up here. But the important point is that the substitution meta-analysis did basically confirm that what we saw in our overall analysis within our own cohorts there, that whole grains were better than potatoes in any form for risk of type 2 diabetes. In the East Lancet Commission report, we were looking at the world's literature, and it included a lot of meta-analyses, but I become much more cautious and maybe a little bit disillusioned with the meta-analyses. I think it's really helpful to pull out of the world's literature all the data we have, so we're not just cherry picking here and there. But most of the studies in those meta-analyses are based on a single measurement of diet at baseline and then follow-up. And this is what we see in our own cohort. We published an analysis on the left there several years ago, looking at type of fat and total mortality in our cohorts. And it's like carbohydrate. The type of total fat just means almost nothing, but the type of fat is really important. And at the top, trans fat, very positive, saturated fat, positive, but much less so. All these compared to total carbohydrate. And MUFA inversely related, and very strong inverse relation with PUFA there. But on the right is what we would see what we saw in our own data if we only used the baseline measurement. We basically missed almost everything. Now, the fat may be a worst case example because this was changing over time, and we updated our database for trans fat was coming and going over time. So processing as well as sources were changing. But we would have missed trans fat entirely. MUFA going in the wrong direction, nothing for saturated fat, just a little bit of weak inverse relationship with PUFA. So if you look at a meta-analysis on this, you will miss a lot. We also looked at this, not yet published, for red meat and coronary heart disease. And one thing we've done really for the first time in the paper on red meat and type 2 diabetes, there's two main types of error here we have in long-term epidemiologic studies. One is the inherent measurement error in our questionnaires and how people respond to them. And we know they'll never be perfect, and not even close to perfect. There's a lot of error. So we spend a lot of time collecting what we call a lifestyle validation study, where we compare our questionnaires with 2 weeks of weight diet records. And so we can calibrate our questionnaire against the diet records. But then, even if we have a perfect measurement of diet over 1 year, which is what we usually ask about, that's not going to be a perfect measure of diet over time because people change their diets. And there's quite a bit of variability in individuals' diets over time. So for that, we've generally taken the average of repeated measurements of diet over time. But only recently we put both of these adjustments together, calibrating each questionnaire and then also looking at using the average of repeated measurements over time. So this is what's lost. Basically, this is what we see: a baseline with one measurement only, processed meat and coronary heart disease, 1 serving a day, relative risk of 1.12. Processed meat, this is unprocessed meat. Here you look at this, you'd say, there's not much going on, pretty null. But this is what we see if we have used a baseline and we then calibrate the baseline measurement. It goes up quite a bit. Here, this goes up, but calibration isn't providing more data, so the confidence interval also goes up if you're only calibrating. This is looking just at repeated measurements without calibration. There's more information. It's much more robust, much more significant, positive, and then there is a pretty potentially important relationship, highly significant with unprocessed red meat as well. And this is what we get if we do both repeated measurements and calibrate. So basically comparing this with what we would get with just baseline uncalibrated, there's, in general, we've seen for at least red meat we miss about 3/4 of the association, relative risk -1, that's the effect, if we only use baseline and calibrated assessments of diet. So it does maybe think maybe there's something I would like to add to meta-analysis, and that's the best telescope principle, I call it. Now, if you wanted to know how many moons does Jupiter have, what would you do? Would you do a meta-analysis of all the papers published since Galileo? How many moons does Jupiter have? 4? The estimates now are varied, but there's somewhere around 80, actually, when you use the best telescope. So there's no one right answer to what study is best. Is it well-powered, which has the best measurement of diet, which has an informative range of intake, which is controlled for confounding? So I think it's looking at some of the, I think people who understand the field do know that these things are important, and some studies do these things better than others. So you'd like to, as well as looking maybe at the summary of all the studies, look at, do you see that same thing, or is it different if you really look at studies that are most powerful? And it may be that for red meat, we have really good data, but if you're looking at soy products, you probably want to go to one of the Asian studies, since we just don't have a good optimal range of intake. And finally, I wanted to just toss out one direction our metagenomics or meta-omics group is going down. This is a paper, I think it's accepted now, but actually PubMed is sort of shut down at the moment. I don't know if you've noticed if you tried to look at something. It's sort of scary, and they could shut the whole thing down. It's well. But basically, this used our data from the lifestyle validation study, where we had 2 weeks of whey diet records on about 1,300 participants in our study, and a lot of biomarkers at the same time. And so we did metabolomics there, got a metabolic signature for carbohydrate. We did a testing and validation training and validation analysis here within the lifestyle validation study. Then we looked at the metabolomic signature for carbohydrate intake in our cohorts where we had metabolomic data, which is about 11,000 participants. And then we also looked at the genetic the genetic risk scores for this signature. So it's sort of putting two omics together here. And I won't go into the detail here, but we did find that there were a lot of SNPs that did predict that signature metabolic risk score for here for diabetes, for carbohydrate intake. But just as a word of caution, although it sounds impressive, we got the genetics, we got the metabolomics, there's still confounding here, maybe even more confounding than our usual dietary intake. So the best predictor here of, I think it's whole grain intake, was actually proline betaine, which there's probably not much carbohydrate there. It's basically a marker for citrus fruit and orange juice, and it's the main predictor there. So it's almost for sure this is because of confounding by citrus fruit intake. So we do have to recognize that confounding is still an issue when we're using these omics data. And then we looked at the metabolomic signature in our total cohorts. This is where we had about 11,000 people again. And there we looked at the metabolomic signature for different forms of carbohydrate intake, again with total carbohydrate, sort of weak positive association, and this is obviously mostly refined starch and sugar, sugar positive, but whole grain, strong inverse relationship here, refined grain, positive association, fruit intake, weakly inverse here, vegetable sources of carbohydrate inverse, strong positive association with potatoes and legumes inverse. So no news here, but it's sort of nice that coming at this from a quite different direction and using omics technology, we get back what we've basically seen in our large cohort studies over time. So anyway, that's a quick view over some of the things that are keeping us busy these days. Thank you.